What I want to do is set maybe high-level vision, share with you some of the ideas I think are the big ideas in feature learning and deep learning. I think of the agenda of deep learning as the idea of using brain simulations to make learning algorithms much better and easier to use, and also make revolutionary advances in machine learning and AI. So come back to this later, but once upon a time, I guess, when I was in high school, I think I joined the field of machine learning because I wanted to work on AI. But somehow that got lost, and instead of actually doing AI, we wound up spending our lives doing curve fitting, which is not what I signed up to do. And deep learning was, for the first time in many years, made me think about the bigger dreams again. I should come back and say a bit more about that. And again, I want to say, the sort of vision and ideas I want to share is really not mine, but is, I think, shared by a large community, including, Jan, Jeff Hinton, Yosha Benjo, many others that you hear from in the next couple of weeks. What do we want computers to do with our data, right? We want to look at images and label them, look at audio, listen to audio and do speech recognition, have text and do stuff with text. And it turns out that machine learning is our best shot at most of these applications today, but it's very difficult to get these applications work, right? So a while back, I asked some of my students at Stanford to use like a state-of-the-art computer vision algorithm to write the motorcycle detector. And this was the result they got. And this is typical in computer vision, right? Even though learning algorithms works, each of those lines is like a 6 months to 2 years of work for a team of engineers. And we'd like these algorithms to be less work to build and also maybe perform better. So let me start to explain some of these ideas using computer vision, and then we'll talk a bit about audio and apply these algorithms to other modalities as well. So why is this problem hard, right? It's so obviously a motorcycle. How on earth could the computer fail to recognize what this is? Zooming into a small part of the image, zooming into where the little red square is, where you and I see a motorcycle, the computer sees this. So the computer vision problem is to look at all those pixel intensity values and tell you that all those numbers represent the exhaust pipe of a motorcycle. Seems like you need a very complicated function to do that. And so how do we do this? So machine learning guys like me say, oh, just feed the data to the learning algorithm and let the learning algorithm do its job, right? When I teach my machine learning class, I draw pictures like this. And this is just not how it works. So let's pick a couple pixels and let's plot some examples, right? So take that image there, and because pixel 1 is relatively dark and pixel 2 is relatively bright, that image has that position in this figure. Now let's take a different example. A different motorcycle image has a brighter pixel 1 and a darker pixel 2, so that second image gets plotted at a different location. And then let's do this for a few negative examples as well, non-motorcycles. And what you find is that if you plot a set of positive and negative motorcycle and non-motorcycle images, that your positive and negative examples are extremely jumbled together. And so if you feed this data to, certainly a linear classifier, it doesn't work. So what is done instead in machine learning is that won't it be nice if you could come up with what's called a feature representation? If you could write a piece of code that tells you, does this image have handlebars in it? Does this image have tires or wheels in it? And if you could do that, then your data looks more like this on the lower right, and it then becomes much easier for, say, a linear classifier, like a small vector machine with logistic regression, to distinguish the motorcycles from the non-motorcycles, right? But the story goes on. So in this illustrative example, I was saying, well, what if we could write a piece of code to tell us if there are handlebars and wheels, but we don't actually know how to do that. And so in computer vision, what is done is actually the following. This is how people actually come up with features in computer vision. This is kind of a notional illustrative example, but this is what I'm going to do. I'm going to take my motorcycle image. I'm going to detect edges at 4 different orientations. So I'm going to look for vertical edges, horizontal edges, 45-degree edges, 135-degree edges. And then what this number, 0.7 in the upper right means, right? That number is saying that the density of vertical edges in the upper right-hand quadrant of my image is 0.7. And what And what this number down here says is that the density of horizontal edges, in the lower right-hand quadrant of my image is 0.5. And in case you're getting the sense that sort of like, oh my God, what on earth is going on here? This seems horribly complicated. How on earth did anyone come up with this piece of code? That's the point. And sadly, this is the way that a lot of computer vision is done today. So more broadly, this notion of a feature representation is pervasive throughout machine learning. And in fact, I guess I live in Silicon Valley, and if you walk around Silicon Valley and look at where people are spending all their engineering time is often in coming up with these feature representations. So let's delve deeper, right? So where do these features come from? Since they're the primary lens through which our algorithms see the world, this gives them a certain importance, right? So how about computer vision? Oh, and in fact, this notion of feature representations is pervasive, for vision, audio, text, even other applications. So where do we get the features from? In computer vision, the state-of-the-art answer for where the features come from is that teams of tens, hundreds, or maybe thousands of computer vision researchers have spent decades of their lives hand engineering features for computer vision. The figure on the upper left is a figure that I took from the SIF paper. The SIF paper is the single most highly cited paper in computer vision in like the last 15 years. And I've read the paper maybe about 5 times now, and I still have no idea what it's doing, right? It's this sort of complex piece of code that David Lowe, is a good friend, David will tell you this himself. It took David literally 10 years. I'm not kidding, he'll say 10 years himself, of filling with pieces of the code in order to come up with the SIF feature, which works pretty well, but you have to ask, is there a better way to design features than this? That's vision. How about audio? Same thing, right? Teams of tens, hundreds, or thousands of audio researchers working on features for audio. MFCC is shown on the upper right. That's actually a pretty clever, surprisingly hard to beat, but again, honestly, to this day, I have a hard time understanding what some bits of the MFCC algorithm are doing. And natural language, in fact, I think most of natural language processing, text processing today, is unapologetically about finding better features. So think about parsers, right? There's a lot of NLP work on parsers. This piece of software that tells you where the noun phrases are in your sentence. I mean, why on earth do I care where the noun phrases are in my sentences? I really don't need software to tell me that. The only reason we spend so much time working on parsers is because we hope that this will give us useful features to then feed to some later downstream application, like anti-spam, web search, machine translation that we actually care about. So common features is difficult, time-consuming, requires expert knowledge, and when working with applications of machine learning, we spend a lot of time. So if you look at applied machine learning, or if you walk at go to the company, look at people doing applied machine learning, this is really what they spend the vast majority of the time on, is coming up with features. So can we do better? So the next piece, in a lot of deep learning, there's like many people, like many of you, I tend to treat biological inspiration with a great deal of caution and even a healthy dose of skepticism. But for me, a lot of my thinking about deep learning has taken inspiration from biology. So I want to share with you, some cool ideas from really biological inspiration. So it turns out there's a fascinating hypothesis that much of human intelligence can be explained by a single learning algorithm. So it's called the one learning algorithm hypothesis. Let me share with you some evidence for this, right? So this was an experiment first done on ferrets in MIT. That red piece of brain tissue shown on the slide, that's your auditory cortex. The way that you're understanding my words now is that your ears is routing the sound signal to that piece of red brain tissue and is processing the sound, and then that's how you eventually get to understand what I'm saying. So neuroscientists did the following experiments, which is cut the wire between the ears and the auditory cortex and do what's called a neural rewiring experiment so that eventually the signal from the eyes gets routed to the auditory cortex. It turns out if you do this, that red piece of brain tissue learns to see. And this is the word see. This has been replicated in multiple labs on 4 species of animals. And these animals can, quote, see in every single sense of the word that I know how to use the word see. These are animals that can do visual discrimination tasks. They can look at things and make correct decisions based on an image in front of them using that red piece of brain tissue. Another example, this red piece of brain tissue is your somatosensory cortex that's responsible for your sense of touch. Do a similar neural rewiring experiment, and your somatosensory cortex learns to see. So more generally, there's this idea that if the same physical piece of brain tissue, right, the same physical bit of your brain can process sight or sound or touch or maybe even other things, then maybe there's a single learning algorithm that can process sight or sound or touch or maybe other things. And that if we can discover some approximation to that learning algorithm, or maybe discover a totally different algorithm but that accomplishes the same thing, then that might be a better way towards making progress in AI than hand engineering separate pieces of code in each of these individual application silos, which we have been doing for decades now. Just a few more fun examples. It turns out you can plug in other sensors to the brain, and the brain kind of figures out how to deal with it. Shown on the upper left is seeing with your tongue, right? So this is actually undergoing FDA trials now to help blind people see, a system called BrainPort. So the way it works is you strap a camera to your forehead, takes a low-resolution grayscale image of what's in front of you, run a wire to a rectangular array of electrodes that you place on top of your tongue, so that each pixel maps to a point on your tongue, and maybe a high voltage is a bright pixel, and a low voltage is a dark pixel. And even as adults, you and I today will be able to learn to see with our tongues in like 10, 20 minutes. Human echolocation. You can either snap your fingers, right, or click your tongue, and there are actually schools today training blind children to learn to interpret the pattern of sounds bouncing off the environment as human sonar. Haptic belt is, ring of buzzers around your waist, program the one facing north to buzz, and then you get a direction sense. You just magically know where north is. Similar to how birds sense direction. And you can plug a third eye into a frog, and the frog learns how to deal with it. It doesn't work in every single instance. There are cases where this doesn't work, but I think to a surprisingly large extent, it's almost as if you can plug in, not quite any sensor, but a large range of sensors onto almost any part of the brain, and the brain kind of learns to deal with it. So wouldn't it be cool if we get a learning algorithm to do the same? So let's see. Let's take a break. Could you guys, I think you now know enough to look at questions 1 through 3 in the handout. Do you guys want to take a few minutes to just write down what you think is the right answer, and when you've done so, discuss what you wrote down with your neighbors and see if you agree or disagree. For question 1, I had D. For question 2, I had auditory cortex learns to see. And for question 3, I don't know, different people have different ideas, I guess. I tend to use the wording that much of human intelligence can be explained by a single learning algorithm, but there are lots of other wordings, lots of other ways of describing it. All right. So, given this, what are the implications for machine learning, right? So if we think that the adult visual system computes an incredibly complicated function of the input, right? It looks at all those numbers and those pixel values and tells you that that's the motorcycle exhaust pipe. And so 2 approaches that we could try to build such a system is, we could try to directly implement this complicated function, which is what I think of as the hand engineering approach, or maybe we can try to learn this function instead, right? And kind of a side comment, maybe only for the aficionados of machine learning, is that if you look at a trained learning algorithm, a learning algorithm after it has trained with all the parameter values, is a very complex thing. But the learning algorithm itself is relatively simple. Most learning algorithms can be described in like half a page of pseudocode. So the complexity of the things we're training usually comes from the complexity of the data rather than the complexity of the algorithm. And that's a good thing, because we know how to get complex data. We just have images all around us. But coming up with complex algorithms is hard, right? So here's a problem that I guess I posed a few years ago, which is, can we learn a better feature representation for vision or audio or what have you. So concretely, can you come up with an algorithm that just examines a bunch of images like these and automatically comes up with a better way to represent images than the raw pixels? And if you can do that, maybe you can apply the same algorithm to audio and have the same algorithm trained on a bunch of audio clips and have it find a better way to represent audio than the raw data. Okay? So let's write down the mathematical formalism of this problem, right? Which is, given a 14 by 14 image patch X, one way to represent the image patch is with a list of 196 row numbers corresponding to the pixel intensity values. The problem I want to pose is, can we come up with a better feature vector with which to represent those pixels? Okay? And if you can do so, then this is what you can do. Here's a problem called self-taught learning, I guess, which is, well, so in traditional machine learning, right, if you want to learn to distinguish motorcycles from non-motorcycles, you have a training set with some, and this is a pain because there's a lot of work to come up with a lot of pictures of motorcycles, right? There's like tens of thousands of them. So in the unsupervised feature learning, on the self-taught learning problem, what you do is instead, we're going to give you a large source of unlabeled images. We give you, an infinite source of unlabeled images. Because of the web, we all have an effectively infinite source of images. And the task is, can all those random images up there, somehow can pictures of trees and sunsets and horses and so on, can that help you to do a better job figuring out that this picture down here is a motorcycle? Okay? And so one way to do that is if we have an algorithm that can look at these unlabeled images and learn a much better representation of images than just the raw pixels. And if that superior representation allows us to then look at a small labeled training set, and if this much superior representation allows us to use a small labeled training set to do a much better job figuring out what this test set image is. Okay? So I guess in machine learning, there are sort of a few common formalisms, right? There's the supervised learning setting, which is the oldest, most standard one that most of you best know. So let's say your goal is to distinguish between cars and motorcycles, right? So in the standard, old school, like 50-year-old supervised learning setting, maybe 30-year-old supervised learning setting, you need to come up with a large training set of a lot of cars, a lot of motorcycles. Okay? About 10, 15 years ago, I think Andrew McCallum, Tom Mitchell, or maybe even others before them, started to talk about semi-supervised learning, the idea of using unlabeled data. And that was exciting, but in semi-supervised learning, as it's typically conceived, the ability to use unlabeled data is great, but in semi-supervised learning, typically the unlabeled data is all images of cars and motorcycles. And it turns out that this is a semi-supervised learning, this sort of model is not widely used because it turns out that rarely do you have a data set of where all the images are, either cars or motorcycles and nothing else, but the only thing we're doing is just missing the label. So this is kind of useful, but isn't widely used. Whereas in what I call self-taught learning, the goal is to take totally random images that may be cars, maybe motorcycles, maybe totally other random things, and to can you somehow use this to learn to distinguish between cars and motorcycles? And one way that I like to think about it is that the first time that a child sees a new object, right? Someone invents a new vehicle, like the first time that you and I saw a Segway, we learned to recognize the Segway very quickly just from seeing it once. And I think the reason that we learned to recognize the Segway very quickly is because your and my visual system prior to that had had several decades of experience looking at random natural images, so just seeing the world. And it was by looking at these random unlabeled images that allowed your and my visual system to learn enough about the structure of the world, to come up with better features, if you will, so that the first time you saw a Segway, you very quickly learned to recognize what a Segway is. Right? So just to make sure you got this concept, could you please look at question 4 and just do that and map this to a new example? All right, so someone called the answer. What first part? A, B, C, or D? Right, second part? And third part? All right, awesome. All right, that was easy. Cool. So how do we actually do this? In order to come up with an algorithm to learn features, let's turn one last time to biological motivation. Turns out that when your brain gets an image, the first thing it does is look for edges in the image, right? So the first stage of visual processing in the brain is called visual cortical area V1. I think Jan might have mentioned this yesterday. And the first thing it does is look for edges or lines. I'm going to use the term lines and edges interchangeably. So in your brain right now, there's probably a neuron that is looking for a 45-degree line, 45-degree edge like this shown on the left with a dark region next to a bright region. And there's probably a different neuron in your brain right now that's looking for a vertical line like this one right here. Okay? So how can we get our software to maybe mimic the brain and also find edges like this? What we don't want to do is code this up by hand, because what I don't want to do is talk to neuroscientists and then work really hard to write hand-engineered software that replicates this. I think what's much more interesting is we can have an algorithm learn these things by itself. And in fact, there is such an algorithm. It's a very old one. It's like a 16-year-old result now due to Osthausen and View called sparse coding. You talked about this a bit yesterday, did you? Okay, cool. So let me go through this very quickly then. Sparse coding was originally conceived as like a theoretical neuroscience model. So Bruno Osthausen will tell you, right, he never envisioned that this would be used as a machine learning algorithm. This was like a theoretical neuroscience result used to try to explain, computations in the brain or something like that, right? And this is how the algorithm works. It's an unsupervised learning algorithm. So the way it works is you feed it a set of m images, x1, x2, up to xm. So each input example is let's say an n by n matrix, like a 14 by 14 image patch. What sparse coding does is it learns a dictionary of basis functions, phi1, phi2, up to phi k, such that each of your training images x subject to the constraint that the AJs are mostly 0, sparse. And then the way this is implemented is with a L1 constraint, when we'll minimize the sum of absolute value terms on the coefficients AJ, okay, like a sparsity penalty term. And so if you do this, then by the way, I think this is the only equation I have for this first hour, so I hope you enjoyed it. So same thing in pictures. If you train sparse coding on natural images, every single time you run it, it'll learn a set of basis functions that look a lot like the edge detectors that we believe visual cortical area V1 is looking for. And then given a test example, given a test image X, right, what it will do is it'll select out let's say 3 out of my 64 basis functions here, and it will take that test example and explain it or decompose it into a linear combination of, in this case, just 3 out of 64 of my basis functions, okay? So speaking loosely, this algorithm has quote invented edge detection, right? The algorithm was free to choose absolutely any basis functions at once, but it chose, if you run it every time, it chooses to learn basis functions that look like these edges. And what this decomposition says is that this image X is 0.8 times edge number 36 plus 0.3 times edge number 42 plus 0.5 times edge number 63. Okay? So if you will, this is saying this has now decomposed the image in terms of what edges appear in this image. And this gives a high level, more succinct, more compact representation of the image. And also probably a more useful one, right? Because it's more useful to know where the edges are in the image than to know where the pixels are. Moreover, this gives us an alternative way to represent the image. Instead of representing the image patch using a list of 196 pixel values, we can instead represent it using this vector of numbers, A1 through A64. These are the coefficients multiplying into the basis functions. And just a few more examples. So the method invents edge detection, learns to represent an image in terms of edges that appear in it. And it turns out that a few neuroscientists have done, Van Hatven and Van de Schaaf have done quantitative comparisons between sparse coding and visual cortical area V1, and found that, it's by no means a perfect explanation of visual cortical area V1, but it matches it on surprisingly well on not all, but on many dimensions. Okay. So that's vision. How about other input modalities? So this is a slide I got from Evan Smith from his PhD thesis work with Mike Lewicki. So what Evan did was he applied sparse coding to audio data. And what I've shown here is 20 basis functions learned by sparse coding when trained on natural sounds. Okay, so this is a grid of 5 by 4, 5 by 4 little audio clips, I guess, audio basis functions. So there's 20 basis functions learned by sparse coding. What he did was he then went to the cat auditory system. So the biologists in Boston had been using electro-recordings to figure out what early auditory processing in a cat does. And for each of these 20 things learned by his algorithm, he found the closest match in the biological data. And the closest matches are shown overlaid in red. So this is the same algorithm that on the one hand gives a decent explanation for early visual processing, and on the other hand gives maybe a by no means perfect, but a reasonable some explanation for early auditory processing as well. And it turns out you can do a similar study on early somatosensory processing as well. This is work done by Andrew Sachs at Stanford, where he collected touch data. So how do you collect touch data, right? So the way that Andrew Sachs did it was, so we hold things with our hands all the time, right? I'm holding this thing, but how do you actually collect data about how I'm holding it? So the way Andrew Sachs did it was he took a glove and he took an object and he sprayed talcum powder all over the object. And then when you take a glove and you hold this object and then you let go, the pattern of talcum powder, on your glove tells you where you came into contact with the object, and moreover, the density of talcum powder actually corresponds a little bit to the pressure. And he not sure why he did this, but he then actually found. So what type of objects do people hold, right? Well, we don't know. And so if you're collecting data, you want to be representative of what animals do. So fortunately, it turns out that there were two biologists that had spent about a year of their lives sitting on some island watching monkeys and carefully documenting every single way that monkeys pick up different things. So thank God I'm a computer scientist, right? And so Andrew Sachs, took that distribution of data, and he, wearing his glove, picked up objects using the same distribution of dross as was documented in these monkeys on an island, and that was his data. I think that story was pretty fun, but totally unnecessary. But to cut a long story short, I guess, so training on data like this turns out that you learn basis functions using sparse coding that are, I should say, by no means a perfect match to what is known, to what is believed to happen in somatosensory cortex, but is maybe a surprisingly good match on many dimensions, right? So that's sparse coding. And could you do 5 and 6 on the handout? So what was the answer for 5? B and 6? What was it for 6 again? Okay, cool. What? B, right? All right, cool. Let's take right. So the bases are the same for every image, but just the coefficients A1 through AK, that are the features for the specific image. Okay. All right, great. So that's sparse coding, and it turns out that there are different ways to implement, sparse coding. And what I just talked about was maybe the original way by Olshausen and Field, like in 1986. There are different ways now. I think Jan might have talked about encoder-decoder architectures. I'll talk a bit more about that later today. But I think this intuition of learning sparse features has been kind of key for, is one of the ideas, I guess, that allows us to learn very useful features even from unlabeled data. I'll come back to this later as well. There are other ways to do it. If any of you are familiar with ICA, actually, how many of you have heard of the ICA, Independent Components Algorithm? Oh, cool, a lot of you, awesome. So it turns out that there's a deep mathematical relationship between ICA and sparse coding. It turns out that the two algorithms are doing something very similar. For me personally, these days I tend to use the ICA versions of sparse coding rather than the version I just talked about. But later today I'll also talk a bit about sparse autoencoders, just different ways of learning sparse features. We'll get to that later. But so what can you do? Instead of, what we just described is one layer of one of these sparse feature learning algorithms, maybe sparse coding, maybe a sparse autoencoder, maybe a sparse DBN or sparse RBM. And it turns out what you can do, really building on Jeff Hinton's work, what you can do is recursively apply this procedure where instead of just going from pixels to pixels to edges, you can recursively apply this procedure and just as you can group together pixels to form edges, you can group together edges to form combinations of edges and group together combinations of edges to form higher level features. So let me show you an example of that. This is an example run by Hong-Lak Lee. He's now a Michigan professor. But what Hong-Lak did was he trained one layer of, there's actually a sparse DBN. And first layer, algorithm learns to group together pixels to form edges. Another level up learns to group together edges to form models of object parts, right? So this was an example of sparse coding trained just on pictures of faces. So the entire data set was pictures of faces, right? And then recursively apply this, the next level up, it learns sort of more complete models of faces. So let me make sure that this visualization makes sense, right? When I have this little square here, shown here, what this little square means is that I have learned a neuron in the first level that is looking for a vertical edge like that one, okay? Going one level up, and I've shown all these rectangles the same size, but higher up features are actually looking at bigger regions of the image, okay? It's just they're resized, all look the same, but one level up, this is actually looking at a bigger region of the image. But one level up, this rectangle here means that at that next level, one of the neurons has learned to detect eyes that look like that, right? And then at the highest level, if you look at the upper leftmost square, say, with that visualization is showing that there's a neuron that has learned to detect faces that look a bit like that person, okay? If you train the same algorithm on different object classes, you end up with different decompositions of different object classes into different object parts, then more complete models of objects. If you train the algorithm on a mix of 4 different classes of objects, so there's an algorithm trained on a data set that includes cars, faces, bikes, and airplanes, then you end up with, at the mid-level, you get features that are shared among the different object classes where, I don't know, maybe, maybe cars and motorbikes both have wheel, tire-like shapes, so you have features that kind of share between multiple object parts, and then the highest level you get object-specific features. Okay? Yeah?
Is there any sort of invariance in that representation? Any sort of translational invariance in these?
I see, yes there is. Because of the nature of the visualization, I showed them as still images, but yeah, there's some amounts of invariance that's hard to visualize. I have a better example later today of where we more carefully document the invariance. So I'll have a better example later. Okay, so what's this good for? When you hear researchers in deep learning like me talk, you see people like Jan and me and Jeff Hinton and tell a lot of stories like these. But so you can learn features. So what is it good for? Well, it turns out the Hollywood 2 benchmark is a standard benchmark in computer vision, where the task is to watch a short video clip and decide whether any of a small number of activities took place in this video. Whether 2 people kissed, 2 people hugged, someone was driving, someone was eating, someone was running, a bunch of activities like that. The field of computer vision has tried out many different combinations of features. Last year, Kwok Lee, student at Stanford, found that by learning rather than hand engineering the features, he was able to significantly outperform the previous state of the art. right? How about audio? It turns out you can apply similar ideas to audio. So this is a spectrogram, which is a different representation for audio. You can take slices of spectrograms and apply sparse coding to that. It turns out if you do this, then this is a dictionary of basis functions learned for speech, I guess. I'm not an expert on speech, but in probably a slightly optimistic reading of these, the basis functions learned by sparse coding correspond roughly to phonemes. It's a slightly optimistic interpretation, I should say. But if under this slightly optimistic interpretation, we say informally that sparse coding has learned to decompose speech data, very loosely into the kinds of phonemes that appear in speech. And moreover, you can take this and recursively apply this idea, just as we saw earlier, to build higher and higher level features. And I guess a few years ago, Hong-Lak Lee, so I guess the timid benchmark is a data set that many speech researchers work on. This is one of those data sets where, if you do 0.1% better, you write a paper. And a few years ago, Hong-Lak was able to, make what corresponded to, I think we worked out something like 2/3 of a decade worth of progress or something on this data set, just by learning it. This chart is outdated. I made this chart, I think, back when Hong-Lak was publishing this paper. Since publishing this paper, Jeff Hinton and others have surpassed this, also using deep learning techniques, right? And then, as I was preparing this talk, I asked my students to help me put together a chart of the sorts of results where, we or others or whatever hold a state-of-the-art benchmark result using deep learning. And there were surprisingly many of them from us at Stanford, from other groups. And I've worked in machine learning for a long time. I've never in my life seen any one technology knock over benchmarks like this quickly. It was just the whole field of deep learning is like knocking over benchmarks like nobody's business. There's actually a lot more than fits on one slide. I think if I put all the ones I'm aware of, it'd be about 3 slides like this. Right? What's left to be done, right? So, and then I know that some of you are, here because you want to learn how to apply these things, and I know some of you are here because you might be even interested in doing research yourselves and writing research papers yourselves in deep learning and feature learning. So I want to share with you, and I'll do this later to talk more about this later today as well. I'll share with you what I think of as a good way, as one of many promising directions in which to take research for deep learning. And I think that's scaling up. So how do we build effective deep learning algorithms, right? How do we get these algorithms to work well? Well, in fact, how do you build effective machine learning algorithms? So let's look back in history, right? About 20 years ago, there were these debates about, we have these different supervised learning algorithms, so no feature learning, no self-taught learning. There's these supervised learning algorithms. And there used to be all these debates about, is your algorithm better or is my algorithm better? So Michel Banco and Eric Brill did one of the studies that most influenced my thinking, where they took maybe 4 of the state-of-the-art learning algorithms of the day. I guess back in 2001, SVMs were not yet popular, so they didn't actually study SVMs. But they took a natural language processing task on which they had effectively unlimited source of labeled data. And they trained 4 learning algorithms and plotted on the x-axis as the training set size, plotted on the y-axis is the performance, is the accuracy. All the algorithms do about the same, is the amount of data you have. And even a, quote, superior algorithm will often lose to a, quote, inferior algorithm if only you can give the inferior algorithm more data to train on. Okay? So I think it's results like these that has led to this maxim in machine learning that says that often it's not who has the best algorithm that wins, it's who has the most data. And I definitely see this over and over in Silicon Valley. If you look at, think about the most commercially successful websites, the ones making large amounts of money and that you use probably every day. Many of those algorithms are incredibly simple. It's like logistic regression. But the secret is that those algorithms were fed far more data than anyone else has, right? So how about, so this is supervised learning. How about unsupervised learning? So Adam Coates, actually who helped prepare this handout, a few years ago, actually a year and a half ago, did this interesting study, right, where he took all of the unsupervised feature learning algorithms of the day that, that various guys like us, I guess, debate, is my algorithm better, is your algorithm better, whatever. And he took a bunch of these algorithms and ran all of them and varied the model size. So for unsupervised feature learning, all of us have a large amount of data, right? If you're doing, if you're learning from unlabeled images, from natural images, you have an infinite amount of data, right? And so the parameter to vary is not the amount of data, is the size of the model. So how many features do you learn? Those coefficients, A1, just in the early example, we had 64 coefficients, A1 through A64 for sparse coding. But let's set that bigger. Let's learn 1,000 features instead, or 10,000, whatever. Let's learn a much larger number of features. And what Adam found was that, the algorithm does matter. Maybe it matters more than, we saw in supervised learning, because these algorithms are less mature. But again, we saw the sort of result where the bigger the model, the better it does. And in fact, one interesting historical aside, so CFAR 10, we actually went back and historically traced out, we like to publish papers saying my algorithm's better than yours, yours is better than whatever, right? Went back and traced out a sequence of papers with, person A publishes a result on CFAR, person B publishes a paper saying, oh, I did better, then person C published another paper saying, oh, I did even better, and then the one says, oh, I did even better, and I did even better. And we traced out a couple sequences of that, of supposedly benchmarks, advances in benchmark that was supposedly due to, oh, my algorithm's better than yours, that's why I do better. And we believe that a lot of those results of the supposed progress was actually because the models got bigger, right? It's not that my algorithm is actually better, it's just, I don't know, Moore's law had more time to work, and so I trained mine better. And so I'm going to write a paper saying my algorithm's better. In the stuff I've done, the one most reliable way to get better results has been to train a bigger model. If I change the algorithm, sometimes it makes it better, sometimes not. But in fact, if I look at the literature, I feel like a lot of work by a lot of different research groups has been in some ways on trying to get these models to just train bigger, right? So in this world of unsupervised feature learning, where all of us have an infinite amount of data, I feel like we're not limited by what data we have. We're much more limited by our ability to process the infinite amount of data that all of us have, right? So, many attempts to come up with more efficient algorithms, parallelization. I say Jan's done very cool work on FPGA and ASIC implementation. I think I'm going to take credit for bringing GPUs to the deep learning world, and so on. There's a lot of work like this. And in fact, looking at this chart, my personal interpretation, which others will disagree with, is that those results were achieved to a very large part because of scalability issues. Right? But this is my personal interpretation, which others may disagree with. Could you do questions 7 and 8 on the handout? So question 7, what do you have? Which ones did you check off? 2 and 3, cool. I'll take your word for it. And for question 8, and I just say, actually for question 8, I checked off everything except DNA computing. That was my answer anyway. Yeah, I thought of putting quantum in there too, but I think someone actually is working on quantum computing. Yes, yeah. Right, cool. So let's see. You know what? There was something else I could talk about. I think I'll do that towards the end. So just to wrap up this piece, I think talk about the high-level vision of less learning rather than manually designing our features. But again, kind of for me, this isn't just about machine learning anymore. This is, I feel like, can we really learn something about AI, especially perceptual AI? I think AI in human intelligence is very broad. I think, we're starting to get a handle on maybe the perceptual part of AI, which is maybe like 40 to 60% of many animal brains, right? So it's a big part of the brain. And so what I'd like to do is I say, thank you for your attention and for your patience with me to do these things. I hope that was somewhat fun. What I'd like to do is let's break, and later on in the next couple sessions, we're going to dive slightly deeper into technical details, go from the basics, talk about neural networks, and build out some of the algorithms. Also, just want to point out that after you later today or whatever, if you want to go through a deeper, highly technical tutorial with exercises and everything, there's one up there. This is the URL is also given at the bottom left of the handout, but you can check that out later after today.